My name is Fernando Gont, and this presentation will be about the results of a security assessment of the Internet Protocol version 6. Just as an introduction of the material that I'm going to present today, it's just basically like a high-level discussion of the results that I got while working on a 2-year project on security assessment of IPv6. This is a brief introduction of the work that I have been doing during the last few years. Basically, it has been about working on security assessment of communication protocols for the UK. For the most part, analyzing protocol specifications, analyzing implementations of those protocols, finding ways to actually attack those implementations, then produce fixes, and to the extent that was possible, in some cases even actually producing some patches to actually fix those problems. So you have a few URLs there where you can find publications that I have done during the last few years and so on. So this is briefly the agenda for this presentation. First of all, I will give like a very brief introduction to IPv6, just a single slide, so that if you maybe just have heard about IPv6 but don't really know what it is about, I will provide a brief summary, then try to do a comparison of both protocols so that if you are familiar with IPv4, you can basically port that knowledge to IPv6, and then get into the, I would say the technical discussion about the security implications of IPv6. So what's the motivation of the talk? First of all, in the event that you have just heard about IPv6 but don't really know what it is about, the idea is that the current internet uses the IPv4 protocol that has 32-bit addresses, and we're basically running out of addresses, which means that we will be having problems with connecting new devices to the internet. So this protocol, IPv6, was developed to actually address that problem. Basically, IPv6 has 128-bit addresses, which means that it should give us enough addresses to connect all the devices that we may want to connect to the internet. The original idea was that we would have deployed IPv6 like about 10 years ago or so, before actually needing it. That wasn't the case. For example, current estimations are that 1% or actually less than 1% of the global internet traffic is IPv6, which is, of course, just a little bit of it. And it's like a very different place from the one in which we would like to be. We would like V6 traffic to be much higher right now. It is not. However, on the upside, or on the good side, most of the general purpose operating systems do have support for IPv6. Which essentially means that if, for example, you wanted to deploy it usually on a local area network, you are able to do it. I would say that IPv6 had been like basically ignored for quite a few years, and this year that situation sort of changed a little bit. That was basically as a result of a number of events that happened this year. For example, if I recall correctly, it was in February, earlier in February this year, that the free pool of IPv4 addresses at the IANA got exhausted. Basically, IP addresses, either before or IPv6, are assigned, first of all, by IANA to regional registries, for example, RIPE in Europe, AIRING in North America, and so on. And the central pool of free addresses at IANA got exhausted. That event actually got quite a bit of press. So in many organizations, they got to know about the problem of address exhaustion as a result of that event. Then in June 8th this year, we had the World IPv6 Day, which basically was about having big content providers such as Google, Facebook, and others enable IPv6 on their production services, which from my perspective wasn't much of a big deal from a technical point of view, but it was important from an awareness point of view. Many people started talking about IPv6, or they started talking within their organizations about IPv6 as a result of the World IPv6 Day. I didn't say that we learned much from the World IPv6 Day, but again, it was important from an awareness point of view. And finally, as a result of the previous two events, basically most organizations started to consider the exhaustion of the local pool of free IPv4 addresses. For example, there are estimations, I don't recall exactly whether it's already exhausted, but for example, the Asia-Pacific region is the first one to exhaust the round IPv4 space. Probably Europe comes next. And then, well, probably Africa and the Latin America and Caribbean region. So these organizations started now to consider the point in which they would actually not be able to get any more IPv4 addresses from the regional registries. So as a result of all of these events, it looks like IPv6 is finally taking off in the sense that most organizations are, at the very least, having some kind of plan about what to do with it. It doesn't mean that they are deploying it right now, but they have something in mind to do actually about it. So what's the motivation of this presentation? If you have ever heard about IPv6, it's highly probable that you have read or listened to quite a lot of myths about it. If we talk about IPv6 in general, you may have heard things such as that it has improved quality of service. You may have even heard things such as it helps with with the consumption of energy. It sounds funny, but actually I have even read that sort of claim from quite a few people, even people that are supposed to work on the technical field. And when it comes to security itself, you have probably heard myths such as that security was considered while IPv6 was being designed. Then there's people that argue that with IPv6 the security paradigm will basically change from network-centric to host-centric, which means that if you have, let's say nowadays, networks in which for the most part security is enforced at the network edge, with IPv6 that will change, and basically you move all the security that you have at the network edge to the hosts. Then there's people that argue that as a result of V6 deployment there will be increased use of IPsec. And, well, these myths could actually continue. From my perspective, basically, they have had a negative impact in the existing IPv6 deployments and in the new IPv6 deployments that are emerging, basically because people start deploying IPv6 with wrong assumptions. So, for the most part, what I will try to do in this presentation is try to analyze most of these myths and try to see they are actually truth, or if there's some truth to them, or if they are basically just myth and nothing more than that. And of course, because of the time constraints, I won't really get into specific vulnerabilities, but actually try to influence the way in which you think about IPv6 security and analyze at the high level some aspects of IPv6 security. So first of all, before actually getting into the technical stuff, it's interesting to actually analyze the context in which we are working on V6 security. Usually when you are given like some kind of technology to analyze its security properties, you basically focus just on the technical aspects. But when it comes to the effective security that you get with that technology, there are usually other factors that come into play. So I have tried to summarize here the ones that I think are most important of all. First of all, we have much less experience with V6 than we have with IPv4. And that's important because no matter how good or bad the technology may be, if the personnel that is deploying that technology is not very knowledgeable about it, probably the quality and the security of those deployments is not going to be quite good. Then there is the one about the maturity of IPv6 implementations. Basically, if you go to any site that keeps a database of vulnerability advisories, you will find at least 100 about IPv4 implementations. And if you look for the same thing but for IPv6, you probably will find like half of it, like 50 or maybe even less vulnerability advisories. And for some people, that's kind of like an indication that IPv6 is more secure than before. But from my perspective, that's actually an indication that we still have to do a lot of work on v6. So eventually, we will have sort of the same number of vulnerability advisories for v6 than for v4. It's just a matter of working more on that and actually get to discover all the vulnerabilities that may still be present in IPv6 implementations. There's also the issue of IPv6 support in security devices. Usually, for example, you have a firewall at your organization. It may be the case that it has this or that feature for v4. And if you try to do similar things, but with IPv6, well, that support is not present. So there's not parity of features in security devices. There are other cases in which maybe a device has similar features for v4 than for v6, but for example, the IPv4 support is implemented in hardware, whereas the v6 support is implemented in software. So depending on where in the network you're deploying that device, that might or might not be an issue. Then another factor is that of network complexity. As we deploy IPv6, the complexity of the internet will greatly increase. First of all, we will basically have two networking protocols in the internet as opposed to just one. So we will basically running IPv4 and IPv6 in parallel. We will have increased use of NATs. And some of you may wonder how come that I'm saying that we will have increased use of NATs if actually many people argue that we have IPv6 to actually get rid of NATs. Well, the thing is that as a result of deploying IPv6, we will actually have to deploy quite a lot of NATs to actually be able to deal with it, with this transition. Then we will have deployment of quite a few other transition technologies. Those may be in the form of tunnels, translation, and others. But the bottom line is that the complexity of the network is going to increase quite a lot. Even right now, if you try, in some cases, if you try to troubleshoot network problems, and let's say that you have some sort of communication that is failing and the host involved are using IPv6 or some transition technology, sometimes it gets like very hard to actually troubleshoot those scenarios because of the complexity. And finally, there's the issue of lack of well-trained personnel, which is sort of related with the first one. But the thing is that not only we have less experience with v6, but there's also usually not that many people that have actually like good knowledge of IPv6. Even when probably by looking at this, you would have like a very negative impression of what the situation is right now. The thing is that for many organizations, IPv6 is the only thing that you have on the table to actually remain on this business, which essentially means that if you want to continue incorporating new customers, you need to give them IP addresses, and the only thing that we have on the table to do that is IPv6. So you will be sort of forced to actually deal with these things. So I will provide a very, very brief comparison about v4 and IPv6. To the extent that it's possible, I usually try to highlight what the two protocols have in common, as opposed to take the attitude of, well, this is a completely different protocol, forget about everything that you know about before. Because actually, in many aspects, or at least at the high level, they are very similar. In most cases, what changes are the small details. So, as I said before, the most important aspect of v6 is the increased address space, 128 bits as opposed to the 32 bits in v4. For address resolution, v4 employs ARP as opposed to neighbor discovery in IPv6. Neighbor discovery is based on ICMP version 6 messages. When it comes to auto configuration in v4, we have basically DHCP version 4 and router solicitation and router advertisement messages. Although I would say that the most widely auto configuration mechanism is DHCP. Many systems don't even support those ICMP v4 messages that I'm referring to. In v6, we have two different auto configuration mechanisms. One is based on ICMP messages, whereas the other one is DHCP version 6, which is analogous to DHCP version 4. For fault isolation, that is reporting network errors, we have in IPv4 ICMP version 4, and similar thing in IPv6. Actually, probably that of fault isolation is one of the aspects in which Then in IPv4, IPsec support is optional, which means that according to the protocol specifications, if you have an IPv4 implementation, that implementation doesn't necessarily implement IPsec. In the case of IPv6, IPsec support is supposed to be mandatory, but the IETF is working right now to actually degrade that requirement to optional, which means that in the future it won't be mandatory to have an IPsec implementation in an IPv6 implementation. And finally, another aspect is that of fragmentation, which in before is performed both at hosts and routers, whereas in the case of IPv6 is only performed at end systems, right, at hosts. Yeah.
What does MLD stand for?
MLD is multicast listener discovery, which is basically a protocol that is used for handling multicast traffic. And the reason for which I mentioned it there in the slide is because when it comes to, for example, neighbor discovery, that of mapping addresses to link layer addresses, IPv6 uses multicast as opposed to broadcast that we have in before, and that basically the reason for which it has to implement multicast listener discovery too. So strictly speaking, what you use for address resolution is a neighbor discovery, ICMP messages, but then you also need to have multicast listener discovery, which I'm not going to discuss it in this set of slides, but there are some versions of MLD that are actually quite complex. So yeah, MLD has its own security implications. Okay, so let's start discussing some of the security implications of V6. And the first one that I will talk about is the implications of IPv6 addressing. So such as a brief overview, as I said before, the main driver for V6 is its increased address space. It has 128 bits addresses. But aside from that, I mean, aside from the address space, address size, basically IPv6 addressing is very similar to IPv4 addressing. You have the addresses aggregated for the purpose of routing. So, of course, you will have longer prefixes, but it's essentially the same. You have different type of addresses, for example, unicast, anycast, and multicast. Unicast, obviously, meaning that it's a single address that identifies a single system, whereas, for example, multicast is a single address that identifies a multiple number of systems. And we also have different address scopes, which means that we have addresses that are only valid on the local link. That's the case of link local addresses. We also have global addresses that are supposed to be unique on the whole internet and so on. And that's exactly the case with before. With before, we also have link local addresses, global addresses, and so on. Probably one of the few differences between before and V6 is that when you look at an IPv6 host, at any given time it's using more than one address of more one type. Okay, so it's usually the case that if you look at the configuration of a single interface in a V6 host, it has a link local address and it may have one or maybe a few more, for example, global unicast addresses. That's probably the only difference between the before and the V6 addressing. So, of all the addresses that are available in V6, the only ones about which I'm going to talk a little bit are global unicast addresses. This is basically the format of these addresses. We have basically a global routing prefix, which is the prefix that has been assigned by your ISP, for example. Then you have a few bits for subnetting, exactly the same as with IPv4. And finally, you have a few bits, 64 bits usually, for the interface ID, which is analogous to the host ID that you have in IPv4. So essentially, the addresses, the structure of the addresses are the same as in before. As I said before, the global routing prefix is usually assigned by your ISP, the subnet ID by the network administrator, which decides how to subnet the network. And when it comes to the interface ID, it's usually assigned by the actual host. It's not like a central server that handles or that assigns the interface ID, but it's actually every host that connects to the network assigns its own interface ID. There are different policies that you can use to select the interface ID. The most common one is what is usually referred to as modify EUI64 identifiers, which put in English means that you basically take the MAC address of your network interface card and you put that address in the interface ID. We just flip in a few bits, but basically what you do is you put the MAC address in the interface ID. There are other ways to select the interface ID. For example, you may manually configure an address and then and then end up with addresses in which the interface ID is all zeros except for the last byte. There are some, in some systems, the addresses are assigned randomly, so they may be a random number, and so on. So what's related with the format of global unicast addresses is that there's usually the myth that you cannot really do host scanning in IPv6. Usually, when you hear this sort of claim, it's because people usually assume that since the IPv6 addresses are so large, for example, you have 64 bits just for a single network, it would be virtually impossible to actually perform like a brute force scan of the whole address space. Even if you talk about a single subnet, I mean a single local network, you'd need to send like lots and lots of packets. Usually the numbers, the estimations are that it would take more than 100 years to actually scan a complete network. So that assumption basically comes on one hand because of the increased address space, but on the other hand because people usually assume that the host addresses are basically selected randomly from the available address space. So while I was studying and analyzing this stuff, I tried to figure out whether that was actually the case. Of course, the address space is much larger, but the idea was to figure out whether the addresses were actually randomly selected or not. Fortunately, there was a paper that was published not that many years ago. It's referenced here in this slide. It's nice. It's a nice reading. And what these guys actually tried to do, they basically connected, I don't recall if it was a web server or an FTP server to the internet, of course, accessible to the public. And what they basically did, they recorded each of the source addresses that were used to access that FTP or web server or whatever. So they tried to figure out if there was any pattern that the addresses were following, right? So these are some of the categories that these guys proposed for the addresses. The first of them is addresses that are based on the MAC address. That means addresses that include in the interface ID the MAC address of the host. There are addresses that include an IPv4 address. There are addresses that, as I said before, these ones that are called low byte, that basically have an interface ID of all zeros and just the last byte varies. There are privacy addresses that basically are random. Other addresses that are, they refer to them as wordy, which means that as a result of IPv6 addresses being expressed in hexadecimal notation, you can form a few words such as deadbeef there. And there are a few other addresses that have to do with some transition technologies. So these are roughly the results that these guys got while measuring how addresses are assigned. On the left, you can see a table that summarizes how addresses are assigned for host. 50% of them were including a MAC address in the interface ID. Then you have 20% of them that were including an IPv4 address. 10% were Teredo addresses. Teredo is a transition technology that is usually implemented mostly in Microsoft products. There are open source implementations, but mostly in Microsoft products. And the rest of the values are mostly marginal. Of course, if you try to add up all of those values, you don't get to 100% because there were quite a few addresses that they were not able to categorize into one category or the other. Now, when it comes to addresses that are employed by routers, the numbers change quite a bit. 70% of the addresses are low byte addresses, which means that the interface ID is all zeros except for the last byte. And the reason for that is obviously that in the case of routers, you usually configure the addresses by hand. So you're not going to select like a random number, but you basically select an interface ID or an address that is easy to remember. So 70% of the addresses are low byte. Then you have a 5% of addresses that are IPv4 based, which means that they include an IPv4 address in the IPv6 address. The reason for that is probably similar to, to the low byte addresses. Let's say that you have an IPv4 router, and you remember its IPv4 address. So it's one possible way to actually select an IPv6 address that is easy to remember is to include the v4 address in the v6 address. And the rest of the numbers, the ones that are worthy, privacy, and so on, they are very, very small. So what are the conclusions to which we can get from these numbers? First of all, IPv6 addresses are not assigned randomly. Actually, if you take a look at those numbers, they are not random at all. So it's not really true that IPv6 makes host scanning attacks impossible. Actually, strictly speaking, probably what they make impossible is brute force scanning attacks, which basically means that if you are going to just try random addresses, well, you're probably not going to get anywhere. But it's still possible to perform a host scanning attack in IPv6 if you incorporate some intelligence in your scanning tools. My take is that host scanning attacks in IPv6 are going to be much less brute force than in before. The reason for which you do brute force scanning attacks in before because it doesn't really make sense to try to incorporate intelligence in the scanning tools. I mean, it's cheap to actually do brute force scanning, but in IPv6, if you don't implement any sort of intelligence in your scanning tools, you're probably not going to be able to find any host that is live. As a data point, I think that, for example, Nmap does not yet implement any sort of like host scanning for V6. Host scanning in the sense of trying more than one address, okay? They do implement, for example, port scanning for V6. That is, given a single IPv6 address, they can tell you which ports are open or not, but they don't implement like anything to actually scan like a whole range of addresses. There are quite a few techniques that could actually be employed for doing V6 scanning. For example, basically leverage address predictability, which means that, for example, you could, let's say that you know that some network selects the addresses starting from address 1 and 2 and so on. Well, you could basically try just those addresses instead of doing a brute force scanning attack. Another thing that you could do, for example, is start trying random addresses, and then if you find an address that is alive, and you know that, let's say that that address corresponds to Realtek interface cards, well, after you found one single address, then you try all the other addresses that would belong to Realtek, because if it's like a large organization, chances are that all of the systems that they have in that network have been manufactured by the same people. And then there are other ways in which you could perform host scanning attacks, like taking advantage of other protocols. It could be local protocols such as neighbor discovery, multicast DNS, and others. But you could also exploit, for example, application layer protocols. One might construct, for example, a tool that looks for, I don't know, torrents and tries to extract the V6 addresses from the torrents. You could, for example, build some kind of tool that searches at online mailing list archives on the internet, and usually if you take a look at the email headers, you could find V6 addresses there. So there are quite a few techniques that you could exploit to actually do host scanning. As a kind of recommendation, when it comes to addressing, my take is that for servers, you don't really care whether the addresses are predictable or not, because usually if you put a server online, it's because you want clients to get to them. But when it comes to clients themselves, it probably makes sense to actually use random addresses so that like brute force scanning attacks become like harder to perform. In any case, the idea is that you shouldn't really rely on the address unpredictability, but if you want a system not to be reachable by other systems on the internet, basically try to deploy a firewall there. So a couple of comments about end-to-end connectivity. And as a brief overview or introduction, the idea is that in the IPv4 internet was based on a core principle that is usually referred to as end-to-end principle, which basically says that the network itself is dumb and all the intelligence in the network is implemented or at the extremes of the network on the host. Also that any node can communicate with any other node on the network, so that if you connect to the internet, or let's say 20 years ago, you could get to any host that you wanted. And also that the network itself didn't care about what was inside the packets that you were sending on the network. Like routers would only take a look at the IP header, but not take a look inside of the contents. This principle, this set of ideas is usually referred to as end-to-end principle, and people usually argue that the end-to-end principle enables innovation. And the reason for which many people argue this is that if the network itself doesn't take a look in what you do inside IP, that means that you can basically, for example, design your own transport protocol and deploy it on the internet easily. However, since quite a few years ago, that principle has been removed from the internet, for the most part as a result of the deployment of NATs, network address translators, which basically violate all of these principles. For example, a NAT by default usually doesn't allow incoming connections to your local network. Usually a NAT also has to look inside the contents of an IP packet because it needs to look at the port numbers, rewrite the port numbers, etc., etc. Which basically means that nowadays, if you want to deploy something on the internet, it usually needs to be TCP, UDP, or ICMP, and we are probably heading in the direction of like everything needs to be over HTTP. Like network don't really let anything pass through if it's not HTTP. Many people argue that since, of course, IPv6 doesn't require the use of NATs because it provides all the IP addresses that we need, that they usually argue that with IPv6 we will be able to actually return to the end-to-end principle. That is, we will move back to having the end-to-end principle in the internet. So this is basically the myth that I'm talking about. And this is one of the reasons, one of the selling points that many people use for IPv6. Like, well, it's not only about addressing, that having more addresses, but also that with IPv6 we could actually simplify the network and get back to the end-to-end principle. However, from my perspective, that's not really going to be the case. Even when with IPv6 we have enough addresses to actually assign one global unicast address to every system that connects to the internet, I don't think that global addressability is going to imply global connectivity, global end-to-end connectivity. The reason for that is that, for example, in most cases, networks don't really care about innovation. They basically are there just to provide some sort of service for the organization in which they are deployed. So as long as they enable the employees, for example, to do email, web, and that kind of stuff, they are fine. Also, there's no actually a requirement to go back to the end-to-end principle because all the applications that the users know about basically can operate even without the end-to-end principle. So there's not really an application that we know that could be possible with this end-to-end principle. So we don't really have a motivation to actually get back to the end-to-end principle. Even then, if you think about end-to-end connectivity, for example, it's probably not like a desired property. For example, in many cases, if you have a home network, you don't really know, you don't really want every of your systems to be directly accessible from the outside. In most cases, what your hosts are doing is simply consuming information from the internet. So in those cases, probably you don't really want to get back, even if you could get back to the end-to-end principle. And what's interesting is that even when people within the IETF, which is the organization that standardizes the internet protocols, even when many of them are in favor of the end-to-end principle, the truth is that last year the IETF standardized some specifications for home routers, and basically what they said is that by default every home router should have a firewall that only allows outgoing connections but not incoming connections. So that means that even the IETF has basically standardized home routers, which would violate this end-to-end principle or this end-to-end connectivity. So the way in which I think that things are heading is that even when you will have global unicast addresses for all your systems, when it comes to connectivity, will be essentially the same as right now. You will only be able to do outgoing connections, but you won't get incoming connections unless, of course, you manually enable that. Few comments about address resolution. As I said before in the summary, in IPv6, address resolution is performed with a protocol called neighbor discovery, which essentially uses ICMP version 6 messages. It's very analogous to ARP in IPv4. So essentially, you have exactly the same vulnerabilities in IPv6 than we used to have in IPv4. It is complicated a little bit because of the fact that since ICMP messages can get fragmented and they can have extension headers and so on, the traffic gets more complex and it's like more difficult to actually deploy countermeasures for these attacks. these are basically the mitigations techniques that you have for these attacks. First of all is the deployment of SEND. SEND is secure neighbor discovery, which is basically adding crypto to neighbor discovery. The problem with deploying SEND, first of all, is that, for example, Windows doesn't implement it. So even if you wanted to, you are not going to be able to protect Windows systems with SEND. And also that it's very hard to deploy. It basically requires a PKI and so on. Then, not to prevent, but to actually detect neighbor discovery attacks, you could do, for example, neighbor discovery traffic monitoring, which should be analogous to what you probably do with IPv4 with ArpWatch. The only difference is that, again, in this case, traffic can get fragmented, so in practice, it's basically useless to do neighbor discovery traffic monitoring. Another option is, in some cases, to add static entries to the neighbor cache, analogous to what you used to do or you could do in before with the ARP cache. Only thing to consider here is that there are some implementations in which even if you add static entries, they don't care about that and they still use neighbor discovery. So you should keep that in mind. And finally, that of restricting access to the local network, which is like general thing and not just for neighbor discovery, which means that to the extent that it's possible, if you can partition the network in many networks, that basically restricts the number of systems that an attacker can attack. So summary with neighbor discovery attacks is that the situation is not really that different from before, but it's actually just a little bit more complicated. Few words about auto-configuration. In V6, we basically have two mechanisms for auto-configuration. Stateful, one of them is stateful, which is the DHCP, analogous to the DHCP version 4. And the other one is what's usually referred to as SLAC, or stateless address auto-configuration, which is based on ICMP version 6 messages. Essentially, the way in which SLAC works is that when you connect the host to the network, it sends a request to any router that might be connected to the same network, and it gets all the configuration information in an ICMP message. So these router advertisements, that are the messages that you get from the routers, contain all sorts of configuration information, such as prefixes, routes, some network configuration, some network parameters such as hop limit, MTUs, and so on. So, of course, the sort of attacks that you could perform against auto-configuration are basically man-in-the-middle and denial of service attacks, which essentially means that you could actually cause all of the traffic to be directed to you, or basically to be directed to a host that does not even exist, so the traffic gets dropped. When talking about the countermeasures that we have available for that, most of them are the same as in the previous case, so I will not talk about them. The only one that is specific for attacks against stateless address auto-configuration is a countermeasure that is referred to as router advertisement guard, which is basically about filtering these messages at switches. And in summary, the idea was that it was standardized by the IETF, it was implemented by Cisco, and it doesn't work. So if you want to know the details, just look for router advertisement guard vulnerability or stuff on the internet, and you will basically get the details for which this doesn't really work. But I'm trying to highlight this because many people deploy this as like the first line of defense against these issues. Couple of comments about IPsec support. Many people argue that IPv6 is more secure than before because supposedly it has support for IPsec. If you look at the specifications, they say that, well, in the case of V4, IPsec support is optional, but in V6, it's supposed to be mandatory. However, this is mostly words on paper in the sense that you have lots of V4 implementations that do contain an IPsec implementation. And we also have, regardless of what the specifications say, we have V6 implementations that don't really support IPsec. And even then, I mean, what's required by the specifications is IPsec support, but not usage, which means that you could have the IPsec support there, but that doesn't mean that the hosts are really using IPsec. So in summary, well, this is really not true, that of V6 being more secure than before, and it's also not true that we are going to have increased use of IPsec just because of IPv6 deployment, even when many people argue about this. Okay. Couple of words about security implications of transition coexistence mechanisms. The idea basically is that the plan that we had for IPv6 was that people, like everybody would deploy V6 10 years ago or so. So by the time that we actually needed V6, it would already be present in the network. So it wasn't going to be a big deal for the IPv4 address space to get exhausted. But the thing is that this plan basically failed. Only a few organizations actually deployed IPv6, and in many cases they deployed it in the core of the network, but they don't really provide IPv6 access to their clients. So the current strategy for V6 deployment is based on a set of transition technologies which basically aid in deploying V6 in environments that are mostly IPv4 only. Most of the stacks that you have available in general purpose operating systems support dual stack, and they also support some form of transition technology. For example, in the case of Windows, it's dual stack, but it also supports Teredo, iSetup, and I think one other, 624. So what are the security implications of these transition technologies? First of all is that they increase the complexity of the network. In many cases, they introduce single points of failure, which means that if you have IPv6 hosts that use these technologies, all traffic needs to go to a single system. So that's going to be a very interesting target for attackers to deny the service to many clients. And then it's also interesting that usually people don't really talk about this, about the privacy implications on some of these technologies. For example, there are many providers in the US that offer like free tunneling services, which means that if you want to use V6, you can get a free service from them. And many people try that and say, oh, that's great, I don't even have to pay for that. In some cases, you don't even need to get an account. But the problem is that all of your traffic is being sent through them, which of course, in some cases, you may not care about, but if you think about, I think that nobody could, for example, think about Chinese vendors or the Chinese government actually tunneling all their traffic through the US, just as an example, right? Another consideration is that of the complexity of the resulting traffic. Here you have probably one of the worst examples. That's the structure of a TCP packet that is being sent on the network by using the Teredo transition technology. The point is that the resulting packet may be very, very complex, have lots of headers, and as an exercise of how complex this can be, for example, for security devices, just try to implement a lead pickup filter for example, detecting traffic sent to a specific TCP port in this case, and it might get like a little bit tough. And finally, some words on security implications of V6 on V4 networks. Usually people think that, well, if my network is V4 only, I don't really care about IPv6. I have not deployed it. But the thing is that, as I said before, most general purpose operating systems, they do have support for native IPv6 and also for transition technologies. So that really means that even if you have what's supposed to be like an IPv4 only network, you really have a partial deployment of IPv6 anyway. The security implications of V6 on V4 networks could be, for example, that an attacker might connect to your network, enable the V6 connectivity in all of your systems, and, for example, leverage that to actually evade some security controls that you might have. And also, there's one technology that I mentioned before that is Teredo, that the goal of Teredo itself is to actually make hosts accessible through a NAT, which means that if you have Teredo running on your local network, that might mean that your host could be accessible from the outside network, even if you are behind the NAT, okay? So, just closing the presentation, I'd like to highlight a few areas in which I think that further work is needed. First of all, IPv6 security or resiliency, if you want. If you look at V6 implementations, they are not mature at all. Actually, as a result of actually testing many of them, basically the idea that you get is that they are at the point in which we were with V4 like 15 years ago. So they failed to enforce validation checks, limits on data structures, and all that kind of stuff. We also need to improve the IPv6 support in security devices. I mean, no matter how good or bad the protocol may be, if you don't have V6 support in security devices, the resultant networks are not going to be much secure. And the last one is about education and training. And that doesn't necessarily mean attending a training or reading a book, but just at the very least, having somebody in your organization at least play with IPv6, read about IPv6, because eventually they will be asked to deploy this in the network. Conclusions? First of all, beware about V6 marketing and myths. There are lots of people that try to sell IPv6 with properties that IPv6 is supposed to have that it doesn't really have them. V6 basically has the same, provides the same functionality as before, but the details are a little bit different, and sometimes those small differences have big difference when it comes to security. And again, the idea is that even if you are not planning right now to deploy IPv6, you should have it in mind because your network has at least partial support of IPv6, and it's very likely that you are going to deploy it in the near term.